Hi guys, welcome to Unit 7. Unit 7 deals with the time of the day, basically the hours and the difference between especially the sidereal day, which is the actual rotation of the Earth around the Sun, around itself, I'm sorry, and also the uh, the so-called solar day because it's based on the position of the Sun in the sky. So what we're gonna do in here, we're going to see the complications basically, which is I just mentioned the fact that there is two things at play here: the position of the sun, which gives us the distinction between day and night, and also the actual motion of the Earth around its own axis. That's basically that defines that motion. And then we're going to talk about noon and the fact that noon is not necessarily the noon that we're talking about, not the 12 o'clock p.m., the one that people usually talk about when they talk about noon. And then describe the hours of the day and how they change from latitude to latitude. Of course, you know that if you are in the northern hemisphere, for example, near the North Pole, there are times of the year where you really don't have much daylight versus there are times of the year also where you don't have much of nighttime. So you have to make that, it depends on how far you are away from the equator. So daylight changes from season to season. And also time zones, the fact that we had to come up with a convention for the time zones, otherwise there will be a conflict in terms of the time, and the daylight savings. So that's basically the topics of the day. Okay, the way we define noon, I'm looking due south for me in here right now in my office. Basically, if I extend my right hand, I know the image is kind of inverted on the screen, but this is actually the west, since I'm looking due south, and this would be then the east. Immediately behind me is going to be due north. If I extend the line from my due south, immediately from the bottom that I'm looking, from the horizon basically, extending about my zenith, about my head, and then going to due north in the opposite direction, that is my local meridian. That is my point of reference, if you wish, from where I am standing. If I stand a little bit to the west or a little bit to the east, my local meridian changes with that. So the local meridian is specific to anybody who is in the same line of sight for me, due south or due north. That is basically the convention we have it. So we define noon is when the sun crosses that imaginary line in the sky. Okay, so when you look due south, going through your zenith, going to due north, the minute the sun crosses that line, when the minute that it's actually in that line, then that is noon. Before it is anti-meridian, before the meridian, before noon, and then after it is the post-meridian or afternoon. So basically, that's how we distinguish night. So the way we agreed on is that, okay, anytime the sun crosses that, that's noon. If I wait the next time that this event happens, which is a day later, tomorrow around noon, that is by convention 24 hours. We agreed on that. We decided that from noon to the next noon, that's 24 hours, or from noon to the previous noon, it was 24 hours. There are some problems with that. First of all, this noon is not the same. Even if we don't change the clock, it changes from season to season. It has to do with the fact that the projection of the sun depends on our latitude, and that differs for almost a minute throughout the season from point to point, from time to time throughout the year. Okay, that's one problem. The other thing also is the clouds. I mean, if tomorrow is cloudy, then my whole thing is a problem. So I really have to come up with a kind of a and then it depends on the latitude and it has to do with that. So there are some inaccuracies in here. But again, I can set up my clock now and say, okay, even if I don't see the sun at this time for one reason or the other, I'm going to call it noon anyway. Okay, so that's how this is called a solar day because it's based on the position of the sun from my vantage point, from my local point in the sky. Okay, as opposed to something else, which is the position of the sun versus the stars. Stars out there. Okay, so and there is a distinction And the distinction has to do with the motion of the Earth around the sun. Okay, let me make the point in here clear from this diagram. For those sitting in Astronomy 125, the lab version of this class, it's an extensive lab where you do the actual measurements. Imagine with me that today is noon, right now is noon, and I'm looking at the sun immediately above in that line of sight, okay, in the meridian, okay? When the Earth makes a full rotation around its own axis and come back the next day, which is almost 24 hours, when it makes a full rotation, so this arrow that you see in here is extending to the stars, which are far away, and our motion around the sun would not change their position relative to us. So we don't really see any distinction. So when we make a full circle, the fact that we made a full circle the Earth makes a full circle around its own axis, and it moved around the sun, the other stars don't care. They're far away, too far for us to be, our motion around the sun to be of any significance. So by that time, that is a full rotation. In order for my line of sight to align itself so that the sun sits on that meridian, I have to wait a few more minutes for that to happen. And that depends on the fact that the Earth does 365 days for 1 year. That means 1 day, it's 1 over 365 of that rotation. So this whole thing from here to here, it's 1 day, which is 1 over 365 days. That's basically what 1 day in a year is. A full rotation is 360 degrees. So that amounts to about a dip of a 1 degree, if you wish. I mean, it's slightly less because 360 divided by 365 is not exactly 1, but it's very close from 1. That difference amounts to about 4 minutes between the sidereal day, which is shorter than the solar day, which is in reference to the position of the sun with respect to my own noon, my own local meridian. So the sidereal in here is referring to the rotation of the Earth with respect to its own axis universally with respect to the stars. So this is the actual rotation. The Earth does only 23 hours and 56 minutes once it's spinning around its own axis. You need the extra 4 minutes to align itself so that the sun is in the same position as it was last time. So that's basically the distinction between the two. Okay? In addition to that, daylight changes depending on the time of the year. And the summer, at least for us in the northern hemisphere, this daylight extends because we have the sun staying far longer in the sky. Let me go back to the first slide. In the summer, the sun rises way deep north compared to still from the south, okay? But up north, relatively speaking, compared to the winter where it starts low, rises to noon, and then immediately go back. So there is a less curve in here for the sun, less daytime, less exposure to the sun, versus in the summer where there is more exposure to the sun, so the daylight extends. The sun rises way early in the day and sets late in the afternoon. Okay, so there is more daytime in the summer versus in the winter where the sun rises later in the morning and sets early in the afternoon. So that means daytime is short. Nighttime, of course, is the opposite. Okay. When we are in the equinox, and we're headed there right now, we're going to February, so we still have about a month and a half to 2 months to get into the winter, the spring equinox, and that's basically where that time. So if you're trying to measure it right now, we are somewhere in here. Okay, not to this point, which happened way back in December, not to this point, which is going to happen sometime in March. So we're somewhere in between, and we're moving this way. Okay, until at some point around June 21st, we're going to be in the extreme, in the summer solstice. Okay, so that's how this the difference between daytime and nighttime is. Make sense? Okay. However, as I mentioned before, there are some points, especially above 66.5 degrees, where there are times in the year where there is very hardly any much nighttime. Mainly it's daytime, and the opposite is true. There are times in the year where there is hardly any daytime, but mainly nighttime. And the opposite is true, of course, for the southern hemisphere. So all of this picture is reversed when it comes to the southern hemisphere. Okay. So as I was saying earlier, keeping track of time is critical, especially in the advent of basically fast-moving machineries, like, for example, trains. People needed to come up with some sort of an understanding. You can't have universal time, because if it's, let's say, for example, 2 o'clock somewhere, and the train needs to arrive an hour later, we don't want to say, for example, so we have to keep track of those schedules, so people started to think in terms of time zones. Okay, so they divided the entire planet in 24-hour time zones. By convention, the line that extends through the city of Greenwich in here, and parts of Europe, Africa, and then the ocean in here, this is the 0 hour. Anything to this side is added to it hours, all the way to something called the date line, which is the opposite of this line. So this is basically the Earth, which is spherical shape. You open it up. Okay. So this line in here of 0 degrees, and this line in here of plus 12 degrees, plus or minus 12 degrees, or plus or minus 12, it's the same line, by the way. That's the date line. That line distinguishes between yesterday and today, or yesterday or today and tomorrow. So this is the date line. Any line on this side is added to it an hour up to 12. Any line on this side subtracted from it an hour up to negative 12. We happen to be in the west coast of the United States, and here we are in California, and that is a negative 8 with respect to the Greenwich, okay, the standard time, the prime meridian. Okay. Our noon is a local meridian. This is the prime. This is the one that everybody agrees on. That this is, let's call it 0 for everybody, and then we start measuring time in here from it. Note in here that all of South America is within a negative 5, which is like when New York, the East Coast is, and more closer to Europe than we are. And that's because the way that this North and South American continents are laid out. But again, we are at negative 8, so we are west of Greenwich line by 8 hours, at least during normal times, okay? So this is basically how if you think about it, how many degrees is one whole hour? You have 360 degrees making a full circle. You have 24 hours also making a circle. Take 360 by 24 hours. That gives you 15 degrees per hour. Okay? And you can do the math and find how many miles that is. So it's about 25,000 miles, basically, the entire circumference of the Earth. So 25,000 divided by 24 is roughly 1,000 miles. So every time zone is about 1,000 miles, so 1,600 kilometers. So if you drive in here, if somebody tells you, hey, listen, New York is negative 5 hours with respect to the meridian, and we are negative 8, okay, with respect to meridian, 8 hours west of the meridian, in a time zone of plus 8. That's the Pacific Standard Time. The Eastern Standard Time is at 5 hours with respect to the prime meridian. So in this case, how much is the distance? Well, 8 minus 5 is 3 hours. There is 1,000 miles per hour. So times 3, that's 3,000 miles. So you can actually deduce distances based on these facts. Because of the fact that I mentioned earlier, that daytime is extended in the northern hemisphere in the summer and short in the winter, some nations adopted the daylight time savings, and that is basically so that lights don't come out early in the night, so that they stay, later, early in the night, early in the day, late in the day, I should say. It's still daylight, basically, and you don't want the lights to come on. So basically, they take extended time in there. And there are other countries where they do the opposite in here. The ones in green, they do the opposite. The ones in the red, they do the daylight. Because their days and nights are completely swapped. I mean, their summers are our winters and vice versa. One thing that I was going to mention, I forgot to mention it earlier when I was talking about the time zones. You see that some lines are not exactly straight lines. They go around and they come back in here, and same thing is happening inside the same country. I guess it's not the same division. Even in the U.S. in here, it's not a straight line coming down. So you're saying, okay, because of the geography, you want all of Greenland to be in the same time zone, so you give it a -3, so although it extends all the way to -1 and extends part of it all the way to -5. That's because you want the same country to have the same clock for political reasons, okay? Geopolitical reasons. That's fine. But how about inside the same country in here? Why don't you have straight lines in here? Because the United States is too big, for example, to have one time zone. So, okay, divided into 3, 4, doesn't matter. Why not have straight lines? It's because of also the geography too. There are some mountains, rivers, whatever determines that. So I just wanted to make this point because these lines, they are all not all straight lines, as this line, for example, is, and this line, or as we thought they could be. Okay. So again, this is Unit 7. Thank you.